This video will include homework solutions for section 8.7. That's our Taylor and Maclaurin series section. And it's also the last section that we cover in Calculus 2. So this is the last homework solutions video we'll have. I'll be doing a selection of problems from 8.7. Quite a few actually, because it's a very long homework assignment. And so I'm going to begin with question number 4. Now in question number 4, they ask us to find the Taylor series for f centered at 4, right? So they want us to find the Taylor series of f with a equals 4. Now our formula for the Taylor series is sigma n equals 0 to infinity. We have some coefficients, and we have x minus a to the nth power. And we learned that our coefficients, right, our coefficients, when we did the work, we discovered that our coefficients are of the form of the nth derivative evaluated at a over n factorial, and then we have x minus a to the n, right? And our radius of convergence, of course, is going to be absolute value of x minus a is less than r. So in problem 4, they tell us this. They give us this, all right? This is given to us. They tell us, right, we're given that the nth derivative evaluated at 4 turns out to equal, and this I'm just taking it out of the book, it says it's -1 to the n times n factorial divided by 3 to the n times n plus 1. Okay, so all we're doing here is substituting this into our formula for the nth derivative evaluated at a. In this case, a is 4. So our Taylor series then for question number 4 turns out to be sigma n equals 0 to infinity. This all goes here. So we have -1 to the n. We have n factorial as a factor. We have x minus 4 to the n as a factor. And our denominator is going to include the denominator from here, n factorial, and then our denominators that we're given here, 3 to the n and n plus 1. And so if we simplify this, right, these factorials cancel, and that gets us to our answer. So we have sigma n equals 0 to infinity, -1 to 11. Times x minus 4 to the n divided by 3 to the n times n plus 1. So that's our answer to number 4 for the Taylor series. And then it says, what is the radius of convergence for this series? So we have if we run, we're going to have to do a ratio test here. So if we do the ratio test, we get the limit as n approaches infinity. Remember, we're taking the n plus first term divided by the nth term, but because we have fractions, we'll multiply and invert the denominator. So this gets us the limit as n approaches infinity. Here we're going to have -1. Well, we don't need the negatives because we're inside the absolute value, so we'll just drop those. So here we're going to have x minus 4 to the n plus 1 divided by 3 to the n plus 1 times n plus 1, which of course is going to be n plus 2 times, and then here again, we don't need the negative 1 to the n. We're going to invert, so we have 3 to the n. We have n plus 1 here, and here we have x minus 4 to the n. Now that leaves us, when we simplify this, of course, the x minus 4, well, this gets us 3. This gets us x minus 4. Those are constants relative to n, our limits in terms of n. So we can bring that out in front. That's going to give us the x minus 4 in absolute value. We don't need the 3 in absolute value. We're going to have the limit here as n approaches infinity. And we have the absolute value of n plus 1 over n plus 2. Of course, this just equals 1. We want all of this to be less than 1 by the ratio test to guarantee convergence. And so that gets us the inequality then. The absolute value of x minus 4 over 3 is less than 1. That leads us to the absolute value of x minus 4 is less than 3. That gets us, just if you want to do just an algebra 2 approach, negative 3 is less than x minus 4 is less than 3. And finally, that gets us, adding 4 to both sides, 1 is less than x is less than 7. For interval of convergence, they asked us for the radius of convergence. Of course, the radius of convergence would be 3. The interval of convergence is 6. The radius goes from midpoint to endpoint, so that's going to be 3. So that's question number 4. All right, that gets us through question number 4. The next problem I'm going to work on is 12. All right, I'm just trying to look at things that might prove to be, a little confusing here. So if we look at question 12, it says find the Taylor series for f of x. Given the value of a, assume that f has a power series expansion. So we do not have to show, right? We don't have to show that the power series we obtain is the actual power series of f(x). We don't have to show that step of showing the limit of r as n goes to infinity of r sub n equals 0. So in question 12, they give us a function. They just give us a polynomial. It's a third degree polynomial. It's x minus x cubed. And they tell us they want a to equal negative 2. So we want a power series expansion for this with a equals negative 2. So we come off to the side and we start with f of x. And then we start our chain of derivatives. Again, remember the chain of derivatives, the ultimate goal here is to find the nth derivative so that we know our coefficients. If we take f of x as given to us is x minus x cubed, the first derivative then is 1 minus 3x squared. The second derivative is going to be minus 6x. The third derivative is going to be negative 6. The fourth derivative is going to be 0, and every derivative after that is going to be 0. Now we evaluate each of these at a. Our a, remember, was given as negative 2. So we evaluate each of these at negative 2. So we put a negative 2 in here, we get negative 2 plus negative 2 cubed. It's going to be 8, but we have a minus there, so that's going to be plus 8. So we get 2, negative 2 plus 8, that's going to give us 6. Here we get 1, now this is negative 2, so negative 2 squared is 4, 4 times 3 is 12. So we get 1 minus 12, so we get negative 11 there. Here we get negative 2 times negative 6, that's just going to be 12. Here, it's a constant, it equals negative 6, and all of these, of course, are going to be 0. So when we want to write down our function as a power series, Remember, the general formula for that's going to be n equals 0 to infinity. The nth derivative evaluated at a, which for us is -2, over n factorial times x minus -2. So that would for us be an x plus 2 to the n. So what do? Well, they want us to write it down. For us, we don't have any nth derivatives. After our third derivative, everybody's 0. So we can just write this down term by term by term. Our first term is going to be the 0th derivative, 0 factorial, x plus 2 to the 0. The 0th derivative is f. So that's going to give us 6 over, technically it's over 0 factorial, but 0 factorial is 1. This is going to be x plus 2 to 0. That's going to be 1. Next, we're going to have the first derivative evaluated at -2. We can get that off our list over here. So that's going to be -11. We're going to have x plus 2 to the first. And then down here we have 1 factorial, which is 1, but we're just writing it out so we can see the pattern. Next comes n is 2. That's our second derivative. Our second derivative is going to be 12. So we get plus 12. We now have x plus 2 to the second because 0, 1. That's n equals 2 term. And then our last term is going to be last because all of our derivatives over here is 0 from now on. Is going to be -6 x plus 2 cubed. And then this is 3 factorial. Those, we can simplify this if you want. I mean, if you want to make it, look as clean as possible, it probably would be best. 2 factorial is 2, so that's just going to be 6. And then 3 factorial is 6, and so this is minus, because that would cancel that, and we get x plus 2. So this is our power series representation of f of x equals x minus x cubed centered at centered at a equals -2. All right, so that was number 12. Next, I'm going to stick with as many evens as possible because I assume, well, I mean, the solutions to the odds aren't in the back of the book, of course, but the answers are. So I'm going to try to stay with the evens. I'm going to do some odds as we get further into the assignment, just because some evens in those sections weren't assigned. So now I'm going to look at number 18. The instructions on 18 are the same as the instructions on 12. But in problem 18, we're given a function that has f of x equals x to the -2. There's an infinite number of derivatives for this. Our previous function terminated after, or the derivatives became 0 after the third derivative. In this case, the derivatives are going to go forever and ever. So here we have f of x equals -2, and it's at, our center is a equals 1. So again, we begin the same way as before. We're going to come over here. We're going to find all of our derivatives. With the goal being to find the nth derivative. So our function is x to the -2. When we take the derivative of that, we get -2x to the -3. When we take the derivative of that, we get -2 times -3 x to the -4. When we take the derivative of that, we get -2 times -3 times -4 x to the -5. And the fourth derivative is going to be -2 times -3 times -4 times -5 x to the -6. And now we want to find the nth derivative. Okay. Well, if we take a look at this term ultimately turns out to be negative. This term ultimately turns out to be positive. Two negatives make a positive. This term again turns out to be negative. So the odd terms are negative. So our -1 to the n will get us odd when n is, will get us negative when n is odd, and positive when n is even. Like here again, n is 4, negative, 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 negative. Turns out to be a positive. Here we have 2 factorial. Here we have 3 factorial. Here we have 4 factorial. Here we have 5 factorial. So we're going to have somebody factorial. And when we take a look at this, on the first derivative, we have 2 factorial. On the second derivative, we have 3 factorial. So we're getting the n plus first factorial, right? Because on the fourth derivative, we have 5 times 4 times 3 times 2 times 1. It's there, but we don't need to write it down. That's going to be 5 factorial. Now, our power on x, for the fourth derivative, we get 6. For the third derivative, we get 5. For the second derivative, we get 4. So we're 2 higher, and it's negative, so we get negative n plus 2. So our nth derivative turns out to be -1 times n plus 1 factorial x to the negative n plus 2. And from here, right, what do we want to do next? We want to evaluate each of these at x equals 1, right? Because that's, or a equals 1. So if we just draw a line over here, so we're going to find f of 1, and then we're going to find f prime of 1, f double prime of 1, f triple prime of 1, the fourth derivative evaluated at 1, and then the nth derivative evaluated at 1, right? That's our ultimate goal, is to get down to the nth derivative evaluated at 1. So from here, we're going to put 1 in here, and that just gets us 1. When we put 1 in here, we're going to get -2. When we put 1 in here, we're going to get -2 times -3. When we put 1 in here, we're going to get -2 times -3 times -4. And obviously, this is going to be -2 times -3 times -4 times -5. That's what we get there. So what are we getting? We're getting, this is positive, this is negative, this is positive, this is negative, this is positive. So we have an alternating sign. So we're going to have -1. Our positives, our evens are positive. So this is going to be just to the n. That will work. And then we're going to get n plus 1 factorial. That's what we have. This is 2, 3, 4, 5. That's n plus 1 factorial. And then, of course, when we put a 1 in here, that just turns out to be 1. So this is our nth derivative. -1 to the n plus 1 factorial. Okay. Now, from here, our next task is to write down our Taylor series representation for this. So we have f of x equals, we have sigma n equals 0 to infinity. We have, if we just write it down, we're going to want the nth derivative evaluated at 1 times x minus 1 to the n all over n factorial. Now, we know the nth derivative evaluated at 1. It's right here. So we're going to put that in. That's going to get us sigma n equals 0 to infinity. And we're going to have -1 to the n plus 1 factorial. Now we have our x minus 1 to the n from there. And then from our formula, we have n factorial down below. And of course, this n factorial and this n plus 1 factorial cancel all terms except for n plus 1. And so we get n equals 0 to infinity, negative 1 to the n times n plus 1 times x minus 1 to the n. And that's it. That's the answer of problem number 18. That's our Taylor series for f of x equals negative x, x to negative 2 at a equals 1. The next problem I'm going to work on is going to be 24. Okay, 24. 24 is one of the binomial theorem problems. They can usually be placed into the I don't like that problem group. And the reason people don't generally like the problems dealing with the binomial theorem is because when you deal with the binomial theorem questions, you have to deal with this combinatoric, which in your book is written as k choose n. Now the definition of this is k times k minus 1 times k minus 2 times k minus n minus 1 all over n factorial. Okay. Sometimes you'll see this term right here written as k minus n plus 1 without any parentheses. I personally like to write it as k minus n minus 1. It just helps me remember the combinatoric better. So we need this, right? Because in problem 24, it says, use the binomial series to expand the function as a power series. So they assume we know, right? They assume we know the power series expansion of 1 plus x to the k. Now, that power series expansion is given. It's in the book, right? It's in, what does Russell call this table? Let me back up here a few pages. He calls it table 1, okay? Table 1. So I'm going to get this from table 1, which is on page 613. Right, 613. This is one of those power series that all of us, right? All of us are just expected to know. So this is n equals 0 to infinity. We have our combinatoric k choose n. And then we have x to the n. This is the binomial series written as a power series. So they want us to use this. And the problem they ask us to consider is 1 minus x, which is not a problem. We'll just write it as 1 minus. We'll write it as a plus minus x. But the power they give us is to the 2/3. And this is where a few of us can start to say, uh-oh, and we start to get a little discombobulated. But there's no reason. We're just going to plug 2/3 in here. So what does this equal, right? This is going to equal the series n equals 0 to infinity. Our k is 2/3, so we're just going to put that right here. Choose n. Now, if you took a statistics class, they gave you this as a combination, right? How many ways can you choose 3 things if there are 5 things in the bag? Well, that's a physical way of thinking about this combinatoric, but the combinatoric equals this, no matter if this is a fraction or not. So we have this, and then I guess I should have taken the time to write this as 1 plus and then put the little minus x in its own parentheses. Maybe that's why I have that little arrow. My brain was telling me I needed to add that intermediate step, and I just didn't realize it yet. So our x right here, it's plus x, but ours is plus minus x. So we get a minus x to the end, don't we? So what does this equal, right? What does this equal? Well, if we try to write this down, right? If we try to write it out, just following the rule that's up here, that's all I'm going to do. What's my first term going to be? Well, if you look in table 1, this works out to be 1 plus, again, we're just reading this from table 1 on page 613. It's 1 plus kx plus k times k minus 1 all over 2 factorial x squared plus k times k minus 1 times k minus 2 now, x cubed all over 3 factorial, and it just goes on and on and on. So we're just going to write ours down. So ours is going to be 1 plus 2/3, that's our k, right? Our k is 2/3, that's going to be 2/3. Our x is negative x though, isn't it? So we're going to put negative x in there. Now we're going to write this term down. Plus, our k is 2/3. 2/3 minus 1 is negative 1/3. We have a 2 factorial down here, and we have negative x squared, because remember, our x is negative x. Plus, we have 2/3, that's our k. We take away 1, that's going to be negative 1/3. We've already done that arithmetic. We take away 1 again, that's going to be negative 4/3. We're going to have x cubed, and down here we have 3 factorial. If we do, oh wow, that was almost a dire mistake, wasn't it? Yeah, I hear you yelling. That's not x cubed, that's negative x cubed. If we do one more term, we're going to have 2/3. We're going to have negative 1/3. We're going to have negative 4/3. We're going to have negative 7/3. We're going to have negative x to the 4th. We're going to have 4 factorial, and this is just going to keep going and going and going. Now, we have to write this as a power series. And this is where experience pays off. When you do these binomial series problems for the first time, it can be kind of daunting to try to match the answer that they put in the book. Because typically the way these work is we focus on this part. These first 2 terms don't really fit a nice pattern. These terms fit a much nicer pattern. And so what you'll see done a lot of times on problems like this is we'll just suddenly do things like this. We'll go 1, right? This is going to be minus 2/3 x. And then if you take a look at this, just this piece right here. If we can get this 2/3 out of the way, I have a 1/3. Then I have a 1/3 of 4/3. Then I have a 1/3 of 4/3 of 7/3. And the next one's going to be 1/3, 4/3, 7/3, 10/3. I've got a nice pattern with these numerators here, 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 and here. They all move up by 3. So there might be an opportunity for me to express that in a general manner. But if I leave this 2 in front of it all, well, that's really going to confuse me, because here I got 2 factorial, 3 factorial, 4 factorial. So I'm going to pull that 2/3 out. Okay, I'm going to pull out the 2/3. And I'm just going to take the time to write down what I have left. This is going to be negative 1 on the top. I'm going to have x squared, aren't I? because negative x squared is x squared. And down here I have 2 factorial. What am I going to have over here? Well, here, this negative and this negative are going to cancel, but I have negative x cubed, so this is still going to be negative. I'm going to have a 1 times a 4, so I'm going to write that. 1 times 4. I'm going to have x cubed. And down here, I'm going to have, oh, I totally forgot this 3, didn't I? So there's a 3 right there, isn't there? There's a 3 to the first right there. I lost that 3. Because here we have this 3 and this 3. So we're going to have a 3 squared. And then we have a 3 factorial. What do we have here? Now remember the 2/3 is gone. We have a negative, and a negative. This is negative x to the 4th. That actually belongs out there. So that's gone for negative 1 to the 4th, positive. Negative, negative. This is also going to be negative. We're going to have a 147 x to the 4th. And down here, we're going to have 1, 2, 3, 3 cubed, 4 factorial. The next term, if you want to write it down, it's going to be 1 times 4 times 7 times 10, x to the 5th. And then we're going to have a 3 to the 4th, because there's going to be 3 under the 1, 3 under the 4, a 3 under the 7, and a 3 under the 10. And then we're going to have 5 factorial. And this is just what's going to happen. Now, at this point, right, at this point, your imagination has to come into play. That's how we work this out. We just work it out with our imagination. We need a power series representation, right? This is the terms written out. If we're going to write this as a power series, it's going to look like this. This is what it's going to look like. We're going to have 1 minus 2/3 x. And then we're going to keep this 2/3 outside. Now, all these are negative, so I'm just going to write that as negative 2/3. Sigma n equals 0 to infinity. And now we just got to make this work, right? The negative's gone. We've got that out front. The 2/3 is out front. This is 3 to the 1st. Now remember, this is when we plug in 0. This is when we plug in 1. This is when we plug in 2. And this is when we plug in 3. All right, that's how it's going to work. So the x, the power on x, is going to be n, and then 2 more. 1 to 3, 2 to 4, 3 to 5. So just writing it not necessarily in the order we normally write it in, but we're going to get x to the n plus 2. Okay. What is our denominator? Well, our denominator, this is when we plug in 0 and we get 3 to the 1st. This is when we plug in 1, we get 3 squared. This is when we plug in 2, we get 3 to the 3rd. So there's one more 3, right? So we're going to have 3 to the n plus 1 there. Now, what about our factorial? Well, we have a 0 gets us 2 factorial, 1 gets us 3 factorial, 2 gets us 4 factorial. So that's going to be n plus 2 factorial. All right, now how do I represent 1 and then 1 and 4 and then 1 and 4 and 7 and then 1, 4, 7 and 10? Well, what we need to realize, right? What we need to realize is that we're going to write something down that gets us 7 when we plug in 2 and gets us 10 when we plug in 3. So if you want 10 when you plug in 3, and the only way to do this is to practice, right? There's no formula, there's no steps that your algebra teacher didn't teach you. You just start thinking, you're like, well, I need 10, so I have 3. So if I took, say 3 squared and added 1, that gets me to 10. Right? Maybe that's what I want to do. Well, does 2 squared plus 1, does that get you to 7? Because that's what you need it to be. And the answer, of course, is no. So that's not a good idea. If I take 3 times 3 plus 1, and then I add 1, right? So here I took 3 times n and I added 1. That got me to 10. 3 times 3 plus 1, that got me to 10. Does 3 right? 3 times 2 plus 1 get me to 7. Well, it does. It does. So maybe this is going to work. Does 1, right? Here n is 1. Does 1 times 3 plus 1 get me to 4? Yeah, oh, it does. So this, right? This is who we have here. So how do we write that? Well, we write it like that. We're going to say 1 times 4 times 7. And then you're going to stop at 3n plus 1. Now, did you hear what I said? I said you're going to stop at 3n plus 1. It's not the case when you do these binomial problems. I'm just going to erase this and so it's a little more distinction. It's not the case that when you do these problems that you take n, plug it in here, and you get 1, 4, 7, and this person. That's not how it works. The convention is when n is 0, you get that one. When n is 1, you get that one plus that one. When n is 2, you get that one and that one and that one. And this just tells you what you're going to get after I stopped listing them. Okay? After I stopped. So since I put the first 3 down, remember, since I put the first 3 down, this one is 0, right? When you plug in 0, this one's when you plug in 1, this one's when you plug in 2. So you don't start using this till you plug in 3, right? It's kind of confusing, but it's just the way the binomial theorem works. And let's be honest, you haven't liked the binomial theorem since the first time you've ever met it, right? It gave you Pascal's triangle. You weren't a fan of the binomial theorem. So there's no reason for you to start loving it now. It's always got its little, bumps and bruises associated with it. All right, so that's number 24. The weirdest thing about number 24, of course, is just doing this combinatoric and then figuring out when to slice it up. I'm going to do later in this video another problem involving the binomial theorem, just because, it's not everybody's favorite exercise when it comes to series work. So that's 24. The next one I'm going to work on is 26. Again, sticking with the evens. It has a new set of instructions, right? It says use a Maclaurin series in table 1 to obtain the Maclaurin series for the given function. So in 26, they give us a function. They give us f of x equals cosine of pi x over 2. Right? Which you and I know is really this, isn't it? I mean, that's all it means, pi over 2 times x. Now we have a Maclaurin series for cosine with just an x. We know it's sigma n equals 0 to infinity, negative 1 to the n, x to the 2n over 2n factorial. It's the easier of the two to remember because we know cosine's even, so it's x to the 2n factorial. Again, where did this come from? Well, it came from my head, but for you, it comes from table 1, or hopefully your head. Because, we need to know how to do problems like this quickly without having to develop the Maclaurin series in this case for cosine. So that we know. And we know the radius of convergence for this is infinity. Now, what do they want us to do? They want us to do this. So instead of having an x in here, we have pi over 2x. So right here, all they want us to do is put in pi over 2x. We're just doing a substitution. We don't have to reinvent the wheel here and go find all the derivatives and do all that work. X here has been replaced with pi over 2x. So we get -1 to the n. Instead of x, we have pi over 2x to the 2n. And here we get 2n factorial. And so now we just clean this up. This is pi to the 2n, so that goes here. We have x to the 2n, so that goes there. And of course, this 2 is in the denominator, so that goes down here. And don't lose your 2n factorial, and that's the entire answer. Because, right, because we knew this power series representation for cosine, sorry, the Maclaurin series representation for cosine, we can just use that as our foundation to build the Maclaurin series for cosine pi over 2. I don't know if it's bothering you. It's not bothering me, but, you know, 2 to the 2n is 2 squared to the n. So I don't know what the answer is. It's even, so it's not in your book. But just in case, you know, that might be written as 4 to the n. No. I don't want that to be the reason you don't understand the problem. All right, so that's 26, and we're done. Right, that's it, we're done. 30, we'll do another one of these because these are kind of fun. 30, the same set of instructions, right? Same set of instructions. They give us f of x equals x squared, the natural log of 1 plus x cubed. Now, we have a Maclaurin series for the natural log of 1 plus x. It's equal to, again, it's in table 1, or hopefully your head. It's n equals 0. No, that's apparently it's not in my head, isn't it? That's sloppy. It's n equals 1. You can't put 0 in here because you get the natural log of 1, which is just 0. So, I mean, it's not wrong if you write it that way, but it starts at 1. We get this, we get -1 to the n minus 1, x to the n all over n. Right? That's our Maclaurin series. The radius of convergence for this one is 1. And so what do they want us to do? Well, they want us to multiply it by x squared. All that's going to do is add 2 over here. But this x has been replaced, hasn't it? By x cubed. They didn't do anything tricky like make it negative, or we would have had to play that game over here. So what are we going to do? We're going to put our x squared, our x squared is going to go here, and then we're going to write down the Maclaurin series for this. That's going to be sigma n equals 1 to infinity, -1. I'm just recopying it from up here, n minus 1. We're going to have n down here. And of course, instead of x to the n, playing the role of x in our new problem is x cubed to the n. So what does that get us? Well, if we clean this up, we're going to have sigma n equals 1 to infinity. We have -1 to the n minus 1, right? I just copied that down. We have n down here. This is x to the 3n, but here's an x squared out here, so that's 2 more x's, right? So we got power to the power you multiply. So this turns out to be x to the 3n times x squared, right? That's what we're doing here. So that gets us x to the 3n times x squared, which is x to the 3n plus 2. And there we go. We're done. So by knowing some foundational Maclaurin series, the ones in table, the series in table 1, right? Then we can build Maclaurin series for other functions rather quickly just by substituting. So in problem 26 and 30, we could have gotten the same answers by doing it the long way like we did in the earlier homework problems, you know, like we did in problems 11, 12, 13, 15, 14, and 18 that they assigned to us where we had to do all the derivatives, but that wasn't the expected process here. The expected process here, because they told us in the instructions, use the Maclaurin series in table 1. So that takes care of 26 and 30. The next problem I'm going to work on is number 42. Okay, we'll work on 42. A new set of instructions, right? That's why I picked it. 42, it's just a standalone problem. It has 2 parts. And it involves the binomial again, so it's good practice for us there. It asks us to expand 1 over the 4th root of 1 plus x, which of course is 1 plus x to the 1/4 power, isn't it? Not positive, negative, huh? Negative 1/4 power. Now, right? We have the power series expansion for 1 plus x to a power. We know that's equal to sigma n equals 0 to infinity. Whatever the power is, in this case, negative 1/4, choose n, x to the n. And that just comes from table 1 again, right? Or our knowledge of the power series expansion of 1 plus x to the k, right? So what are we going to do? Well, what do the instructions say? They say expand this as a power series. So they want us to write this out. Okay? They want us to write this out. So what does this equal? Well, if we start writing out term by term, because of the binomial, our first term is going to be 1. Our next term is kx. K here is negative 1/4 x, right? Then we get to the whole combinatoric thing. So we get k, which is negative 1/4. And then we get k minus 1. So that's going to be negative 5/4. We get x squared. And then our denominator, right, is 2 factorial. This is just the same combinatoric we wrote down when I worked on the previous power series expansion problem. I think that was problem, what problem was that? 24, problem 24. So what's our next term going to be? It's going to be plus, and we're going to get negative 1/4, of course. Then we get negative 5/4 because we take away 1. Then we take away another 1. So we get negative 9/4, right? X cubed, all divided by 3 factorial. And if we do one more term, right, that's going to be negative 1/4. Then we take away 1, negative 5/4. Then we take away 2, negative 9/4. Then we take away 3, negative 159. They're going by 4s, huh? 13/4. X to the 4th all over 4 factorial. So if we clean this up, right? If we clean this up. Now, if we take a look at this, right? We take a look at this, just like we did last time. Right? We take a look at it like we did the last time. We try to figure out where should I slice it up, right? The last time, we had a 2/3 here out in front of this, and a 2/3 here out in front of this, and a 2/3 here out in front of this. But there wasn't a 2/3. So, but this one, we have 1. Then we have 1, 5. Then we have 1, 5, 9. Then we have 1, 5, 9, 13, right? Well, if I pull out the 1/4 here, that's not going to help me because I'm going to start at 5 and then 9 and then 5, 9, 13. I need the 1. I need the 1. So I'm not going to pull that out like we did the 2/3 last time. Here I have 1/4, right? 1/4. So that's 1/4. I'm counting 4s now, in case you don't understand. I'm counting apples, but instead of counting apples, I'm counting 4s. I have 1/4 here. I have 2 4s here. I have 3 4s here. I have 4 4s here. So I don't think I want to chop this term off like we did the last time. I think we're just going to work with that term. We're going to go 1, right? And then we're going to try to write this as a power series plus. And let's see what happens. This is positive, right? This is negative. That's negative. That's positive again. 1, 2, 3, 4 negatives. That's positive. So if we keep this, it's alternating. Negative, positive, negative, positive. So we're going to make this -1. Right? And let's try to see if we can get it to start at 0. Let's see if we. It's always easiest if they start at 0. So we can try to see if we can get it to start at 0. If we try to get it to start at 0, this is going to be -1 to the n plus 1. Because why? Well, because if I make it n, right? Say I make this n. I mean, this is how you build these things. You just try things out. It's like putting together pieces of a puzzle. You see if they fit. So if I do n here, and n is 0, then that's going to be -1 to the 0. That's going to be positive. So I'm going to have to make this n plus 1. Okay, that's not the end of the world. But maybe it's better if we start at 1. I mean, let's just see as we go through. I don't know. I don't know. I haven't done this yet. But as we go through, is it going to be better to have a 0 here and an n plus 1 up there? Or is it better we have a 1 here? And I don't know. We're just going to try. Okay, we're going to try. Now, what's our denominator going to look like? Let's take a look at the denominator, right? Now, remember, we're starting at 1, right? We're starting at 1. I'm going to put the little numbers up here to help us. This is the person when we plug in 1. This is the person when we plug in 2. This is the person when we plug in 3. This is the person when we plug in 4, right? Because we started at 1. So that's 1, 2, 3, 4. If we started at 0, this would be the person at 0. It wouldn't be wrong if you did it with 0 and I do it at 1. We're getting the same thing. Nothing's going to be wrong. There's no error there. I'm just trying to make it look as pretty as possible. That's all. And I haven't seen the answers, so this is just, trying it out like this. So I'm starting at 1. This is 1. So I have 4 down here, right? To the first. Here, it would be 2. We would have 4 times 4. Here would be 3. We have 1, 2, 3, 4s. Here would be 4. We'd have 1, 2, 3, 4 4s. So if we do n is 1, this just turns out to be 4 to the n. Okay. Now, again, right is right, right is right. If instead you started this at 0, you would have to make this n plus 1, right? Okay, that's fine. This would be 0, right? This would be 0, but you need 1, 4. So you would have to make this n plus 1. So it looks like if we started at 0, again, it would be correct. There's nothing wrong in this way of expressing the answer. But then we'd have an n plus 1 and n plus 1. It just looks easier because we don't need all these if we just make this 0. That's the rationalization. Again, if you made that 1 and that was plus 1 and that was plus 1, you're going to get full credit. You're going to get full credit. So if we start at 1, that's 4 to the first, bang. 4 to the second, bang. -1 to the second, positive, like this one's supposed to be. Then it looks like we're going to get x to the, what's our power going to be? Well, here we have a 1 and we get a 1. Here we have a 2 and we get a 2. So that's going to be n as well. So this is starting to feel like we should have done it this way, right? And then remember, we're doing the binomial. We're doing the binomial. And the way we do the binomial is we write these people down. 1 times 5 times 9. And then we go dot, 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 times. And then how do you come up with the, the thing? The general expression. Trial and error. Right? Trial and error. So when we plug in a 3, we need a 9. Well, the easiest thing there to think of is, well, when I square 3, I get a 9. But that doesn't work here because when you square 4, you don't get a 13. Right? When you square 2, you don't get a 5. So now maybe we go attack the 2. I need 2 to get me to 5. Well, I could go 2 times n plus 1. Does that work? 2 times 2 plus 1 gets me to 5. But does it work with 3? 3 times n. That's supposed to get me to 9, right? That's what we're trying to get to, 9. 3 times 2 is 6. 6 plus 1 is 7. Oh, so this doesn't work. Do we do something like 3n? Now remember, 2's got to get me to 5. 2 has to get me to 5. All right, these didn't work. 2's got to get me to 5. So if I put a 2 in here, I get 6. So if I do a 3n minus 1, 2 times 3 is 6 minus 1, that gets me to 5. Okay, that's good. But what about 3? 3's got to get me to 9. 3 times 3 minus 1 gets me to 8. Right? That doesn't work either. So 3n didn't work. Okay, what about 4n? It seems kind of silly, but maybe 4n, right? 4n. 2's got to get me to 5. 2 times 4 is 6. Well, how do I get from 2 times 4 is 8? Sorry about that. 2 times 4 is 8. I got to get to 5, so I'd have to subtract a 3, right? Subtract a 3. Now that does work. 2 times 4 is 8 minus 3 gets me to 5. What about 3? Now 3's got to get me to 9. 3 times 4 is 12 minus 3. Ooh, wait, hold on. 3 times 4 is 12 minus 3. That gets me to 9. So it works there and it works there. But 4 has to get me to 13. 4 times 4 is 16 minus 3. Okay, that's what it is. It's 4n minus 3. And because it's the binomial, remember, we haven't changed x. X is still x. We didn't make it 2x or 4x or pi over 2x. The binomial expansion converges when the absolute value of x is less than 1, and we don't have to clean that up or alter that because our x is still x. If they would have put a 2x, which they did not, right? They did not in the problem. If they would have put a 2x here, well, then all these would have been 2x, 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 and we would have put a 2 in here, and we've gotten x is less than a half. But they didn't. All right. So that's 42, right? 42. Now, from here on out, most of the homework problems are odd, right? Most of them are odd. So I'm going to do 47 next. Oh, I totally forgot about the other half of 42, right? There was 42A and 42B, right? Wasn't there 42A and 42B? There was 42A and 42B. 42B says use part A to estimate. Oops. Okay, so we want to estimate 1 over the 4th root of 1.1 to 3 decimal places. Okay, so this is 1 over the 4th root of 1 plus point. Silly Kevin. 1 plus 0.01. So for us, x equals 0.1, right? That's what's important. Now, let's see if I can remember what our series was, right? That would be really nice if we can pull that out. It was 1 plus sigma. We did all that work to decide that was 1, right? And then we had 4 to the n down here. I remember that. We had x to the n up there. I remember that. We had n factorial down there. And then this, I just erased it. It was 4n minus 3. So we had 1 times 5 times 9 times times 4n minus 3. I really hope that was the actual series because, oh, it was alternating, right? It was alternating. I left out the -1 to the end. All right, there we go. I'm pretty sure that was our series. I'm hoping it is because I'm going to do the rest of the problem assuming it was. So it's an alternating series. And we have the alternating series estimation theorem, or the error theorem for the alternating series. Remember what it says? It says the error is less than the very next term. The error is less than the very next term. So what do we need to know? Well, we need to find out what term's going to get us an error that's smaller than 0.00. They said correct at 3 decimal places. So we need a sub n, that term, to be less than 0.001, 3 decimal places. The easiest way to do this, is not that, just make a chart. Here's n, and then here's a sub n. When n is 1, right? When n is 1, the next term, if you remember when we wrote this out, this was 1, I think it's minus 1/4. Minus 1/4. That's the first. And then the next term would have been, it's all nice, it'll be plus. And then we have 1 times 5, reading it off of here. We had 4 squared, and we had 2 factorial. And then the next term would have been minus. We'd had 1 times 5 times 9. We'd have had 4 cubed, and we'd have had 3 factorial. And the next term was 1 times 5 times 9 times 13. We'd have had 4 to the 4th, and we'd have had 4 factorial. These were the first few terms, right? So when we plug in 1, we're finding the next term, right? So we plug in 1, n is 1. So this is going to be this term. X for us, don't forget x. So this is going to be negative 1/4 times 0.1. That's our x. And that equals, I already did these. I think I have them written down over here on a piece of paper somewhere. I did these on a calculator earlier today. So this turns out to be negative 0.025. Okay, that's not small enough. So when n is 1, our next term, which is, the error is smaller than that, right? The error is smaller than the next term. So that's not enough. So if n is 2, right, we got to do 2 terms, right? We got to do 2 terms. So we're not adding them up over here. We're just trying to figure out what the error would be if n is 2. So we would get 1 times 5, and then we would get 4 squared, 2 factorial, and then here we have 0.1 squared. And then if I did that work earlier, and that comes out to be 0.0015625. That's not smaller than 0.001. So this is where the third term, if we have this be if we only go to 2 terms, our error is going to be less than this. If we use this, our error is going to be smaller than that. And that turns out to be, we don't care about the negative, but it turns out to be negative 1 times 5 times 9, 4 cubed, 3 factorial, 0.1 cubed. And I did that arithmetic, and that comes out to be negative 0.0001172, which is less than 0.001, which is what they gave us. So we can get our approximation to be accurate enough just using these terms right here, 1, 2, 3, and have that be our error. So we know that 1 over the 4th root of 1.1 is approximately equal to this person, the first term, 1, minus that person, which we just found out right there, right? Minus 0.025, plus this person, which we calculated right there, plus 0.00152625. And I think I did that earlier with the calculator as well. And you come up with 0.9765625. And then just you know, because we can, I actually calculated this, the exact value using a calculator. The exact value of that turns out to be 0.9764541. And if you subtract these two, right, the difference equals the error, because this is the estimate and this is actual, right? The difference equals the error. And when I did that subtraction, I got, in absolute value, I got 0.0001,084. So what does that mean? Here's what it means. If we needed to estimate this, we don't have a calculator, right? I mean, yes, this is going to require some arithmetic. I understand you and I grew up, well, I didn't, but you grew up doing arithmetic on a calculator. I'm so old, I predate calculators. When I was in high school, the really rich people had calculators, and of course they only went plus, minus, times, divide. And if you had uber bucks, your calculator had a square root key. Nowadays, of course, calculators are practically free. You can get them in a box of Frosted Flakes. So, but if we had to figure this out, and we didn't have a calculator, and we're willing to do arithmetic, we can do it with this arithmetic right here. And how accurate are we going to be? This is our error. So if you're curious as to, does anyone ever use power series for anything? Well, for hundreds of years, people use power series to do this. Yes, we don't need that anymore, but I'll show you something here it might be even the very next problem. I don't know. Where, you and I in the modern age, yeah, very next problem I'm going to do. We still need power series to help us do some things, right? If we don't have a calculator here. So here we're able to do this kind of root using a power series to this kind of accuracy with just arithmetic. That's what a power series does for us mathematically. It allows us to take something that's not a polynomial, and yet we can develop a polynomial that will give us a very good approximation of that. And the next problem I'm going to work on is 47. It's another example of this. I mean, this is not a polynomial. It's an integral. I mean, it's a number, it's a definite integral, so it's a number, it equals something. We can plug that into, a computer algebra system, and we can get a number for that. But if we don't have a computer algebra system, we can still integrate that. You and I can integrate that. It's not that hard. Because you and I, can find a power series for this. We know that x cosine x cubed is equal to, and we can pretty much write this down without doing any work, but we'll go ahead and go through the steps. That's the power series, right? That's the power series for cosine. And I put x cubed in place of x, and I put the x out here. And then if we just clean this up, right? If we just clean this up, n equals 0 to infinity. 3 to the 2n is 6n, right? But there's one x right there. So that gives me -1 to the n bracket x to the 6n plus 1 all over 2n factorial. Which means the integral from 0 to 1 of x cosine x cubed dx, which we can't do with any technique we possess, is equal to nothing more than the integral from 0 to 1 of this. But you can integrate that. That's just x to a power. This is a constant. This is a constant. So the integral of this is equal to -1 to the n. You add 1, x to the 6n plus 2. You already had a 2n factorial down here, and you divide by 6n plus 2, you evaluate it between 0 and 1. Well, when you put a 0 in here, this is x, right? This is x. 0 to this is going to be 0. All these terms disappear, right? I forgot the sigma. All these terms disappear when x is 0, because when x is 0, this is 0 to the 6n plus 2. When n is 1, it's 0 to the 8. When n is 0, it's 0 squared. When n is 1, it's x, it's 0 to the 8. When n is 2, it's 0 to the 14. They're all 0. When x is 1, this is 1. For every power of n, it's 1. So this is literally equal to, this integral turns out to equal this. N equals 0 to infinity. -1 to the n. When I put a 1 in here, I get 1. For every value of n, I just get 1. So I don't even need to write that down. And I get 2n factorial times 6n plus 2. Now, it says to find this within 3 decimal places. It's exactly the same problem we did last time. We're just going to write this down. We'll write down some terms. Why is it exactly the same problem? It's an alternating series again. So we're going to use the error is less than, right? The very next term. They want it to be within 3 decimal places. So it's exactly the same problem we did in problem 42. But now we're just doing it with an integral. Same question. So if we write these terms down, right? Well, we don't even need to write them down. Let's just do our little table. N is 1, a sub n. So the first term is going to be -1, right? It's going to be 2 factorial. That's 2. So we get -1, we get 2, and we put a 1 in here and we get 8. That's -1/16. And if we grab a calculator, right, I got one right here. We grab a calculator and work this out. Well, we all know what -1/16 is. That's -0.0625, right? When n is 2, we're going to get the second term, right? So that's going to be 1 on top. We have 4 factorial. 4 factorial is 4 times 3 times 2, right? 4 times 3 times 2, that's 24. Right? That's 24. And then n is 2. So this is 6 times 2 is 12 plus 2, that's 14. So we get 1 divided by 12 divided by 14. And that comes out to be 0.0029762. That's not less than 0.01. So, but it's getting close. So this is probably 3 is going to be the winner, right? We plug 3 in here because we're checking the third term, right? Because we have, remember, it's going to be a sub 0 plus a sub 1 plus a sub 2 plus a sub 3. We're just trying to figure out, what do I have to add it together so that this thing is less than 0.001, and that's my error is going to be less than that, and then that's going to be my sum, just like the last problem. So if we plug a 3 in here, we're going to get a -1 on the top. We don't care about that because we take the absolute value anyway. Plug a 3 in here, we get 6. 6 factorial. 6 factorial is 720. Trust me. and then where do we go from there? Here we're plugging in a 3, so this is 20. So we get 1 divided by 720 divided by 20, and that equals, now we're there. We get 0.1234694. So if again we take the first 4 terms, right? And we are first, we take these terms and put them together, then we're going to get our estimate. So it's exactly the same arithmetic as before. I'm not going to go through the arithmetic. All right, so that's 47. There's a group of problems at the very end, right? There's like 4 problems. They assigned 59, 60, 61, and 62. So I'll do 60 and 62, and then that'll be it. The video will end. So we look at 60. Now these problems, they seem to be a lot more than they are. I mean, they're at the end, and so we have this inherent understanding or this inherent belief that they're going to be complicated. Yeah, they're not complicated. And you know they're not complicated because the instructions don't say find an approximation of this sum. It says find the sum of the series, find the sum, right? The sum. So we're supposed to be able to say this equals a number, right? A number. By the way, it equals √3/2. Just looking at it, it's the square root of 3 over. That's cosine of pi/6. I mean, that's what we're supposed to be able to do with this problem. You're supposed to look at that and go, oh shit, that's cosine, cosine pi/6. How do you know that? Well, it equals this. It's got the 2n factorial of power of 2n. That's cosine. This is how do you know? Because I know that table 1 by, well, it's not something that I kind of memorized. I know what table 1's power series or Maclaurin series are because you need them. So this is this. These people have the same power. That's pi/6 to the 2n. That's x equals pi/6. And this, therefore, is cosine of pi/6. And I'm pretty sure that's √3/2. Now, we all know I'm not really good at this triangle, so I'm going to go 1, 2, square root of 3. This is pi/6. Cosine is √3/2. That's all you're supposed to do on number 60. It's not supposed to be hard. Just because it's number 60 doesn't mean it's the most demanding. It's like the simplest question in the homework. And I'm assuming, I haven't done it yet, but I'm assuming 62 is going to be the same way because it has the same thing. It says sigma, oh, it's even easier. N equals 0 to infinity, 3 to the n over 5 to the n, n factorial. This is sigma n equals 0 to infinity, 3 over 5 to the n over n factorial. Well, you have a series in table 1 that looks like this. X to the, this is e to the x. This is e to the 3/5. Because x is 3/5. That's all you're supposed to do. Lord forbid one of your instructors puts a problem like this on the midterm or the final and you leave it blank. Right? That certainly says I didn't memorize, learn, and understand table 1. All right, so that's it. We're done. That's problem 62. It's the last problem in the homework. So it's a good place to stop. All right, I hope this video helps.